Okay, so today we are really pleased to welcome Dr. William Gray. Will completed his PhD in paleoceanography and geochemistry at UCL between 2010 and 2014, before moving to the University of California, Santa Barbara for his first postdoc position in 2014. In 2016, Will returned to the UK to take up a research position at the University of St Andrews before moving to LSCE in Paris in 2018, where he is now a tenured research scientist. Will's research focuses on the development and application of foraminiferal trace element proxies, in particular the use of planktic foraminiferal magnesium calcium, both as an accurate paleothermometer and a proxy for carbonate system parameters, and the use of boron isotopes in planktic foraminifera to reconstruct paleo-CO2. Will's research also focuses on using basin-scale compilations of planktic foraminiferal oxygen isotopes and climate models to investigate changes in atmospheric and surface ocean circulation over deglaciations. The title of Will's talk today is Poleward Shift in the Southern Hemisphere Westerly Winds, Synchronous with the Deglacial Rise in CO2. Welcome and thank you so much for coming to talk to us today, Will. I'll hand over to you.
Okay, thank you very much for the introduction, and thank you very much for to the organisers for the invitation to present to you today. So I am just gonna turn off my my video before I start the talk, and yes, so today I'm going to be talking about recent work that we've been doing looking at shifts in the Southern Hemisphere westerlies over the last deglaciation and their link to rising atmospheric CO2. So the Southern Hemisphere westerly winds play a very important role in helping to close the deep overturning circulation and thus regulate the exchange of carbon between the deep ocean and atmosphere. So south of this figure here is showing a cross-section through the Southern Ocean, an idealized cross-section to the Southern Ocean. And what we see, and so south of the peak in westerly wind stress, the winds drive divergent Ekman transports in the surface ocean, which lift deep waters and tilt the isopignals. Now, eddies try to counteract these steepened isopignals and flatten them out, and they drive a circulation in the opposite direction. But the counteraction of the wind-driven circulation by the eddies is incomplete, and we end up with this residual circulation, which brings nutrient and carbon-rich deep waters back to the surface in the Southern Ocean. And so we get these really high surface nutrient concentrations in the Southern Ocean. And here I'm showing surface phosphate. And so because of iron and light limitation, these nutrients are not completely utilized before being exported back to depth as Antarctic bottom water, which then fills the ocean with these preformed nutrients. And this represents a major inefficiency or a major leak in the biological pump. So essentially, these are nutrients that get sequestered away in the deep ocean without photosynthesis having a chance to use them and draw down CO2. So a mischance for the biological pump. And from modeling and theory, we know that the ocean's preformed nutrient inventory really acts as a master control on atmospheric CO2 on sort of glacial interglacial timescales. This plot is showing that the mean preformed phosphate concentration of the ocean versus atmospheric CO2, both from theory and from biogeochemical models. And so it follows that if we can reduce the preformed nutrient concentration of Antarctic bottom water by reducing the supply of nutrients to the surface from the winds, we can have a large impact on atmospheric CO2. And so records of nutrient utilization based on nitrogen isotopes and productivity from the Southern Ocean indicate large changes in the supply of nutrients to the surface ocean in the Southern Ocean over glacial interglacial cycles, with a reduction in nutrient supply to the surface of the Southern Ocean during glacials. And so while it has long been hypothesized that the winds may play a role in driving these changes in nutrient supply and ultimately driving glacial interglacial changes in atmospheric CO2. And this idea really goes back to Togweiler in 2006, actually being able to test this hypothesis and assess the role of the Southern Hemisphere westerlies in driving glacial interglacial changes in CO2 has been very, very difficult, because we don't really know how they've changed, how they've shifted in the past. So this is what we're trying to address with this work is what is the role of the westerlies in driving glacial interglacial changes in CO2, and particularly we want to constrain how the westerlies have shifted over the last deglaciation. So the kind of state of the art of our knowledge on how the winds have shifted is this compilation from Kofeld et al. In 2013, and they put together a huge compilation of kind of diverse proxies which relate in some way to the winds or the storm track. So moisture, dust, sea surface temperature, and export reduction. And they suggested that in many of these proxies, there was a signal of an equatorward shift in the winds. However, relating kind of measured these proxies, moisture or dust or export production, back to the winds even in a qualitative manner is very challenging, such that even the sign of the change, whether the winds were equatorward or poleward during the LGM, is still widely debated. So that's what we're trying to answer with this work, is how have the winds shifted over the last deglaciation? So to answer that, we turn to the kind of dynamical link, the coupling between the meridional gradients in sea surface temperature and the westerly winds. And so this map here is showing the meridional sea surface temperature gradients overlain with contours of zonal wind stress. And you can see very broadly that we have the steepest sea surface temperature gradients in the mid-latitudes, where we have the westerly winds. And so this two-way coupling arises between the mid-latitude meridional sea surface temperature gradients and the westerly winds at the hemispheric scale, because where we have the steepest gradients in sea surface temperature gradients in the mid-latitudes, this elevates the baroclinicity in the lower atmosphere, essentially destabilizing the lower atmosphere, which anchors the storm track and the westerlies. We then get a feedback because the wind-driven circulation then shapes the wind-driven surface circulation, then shapes the sea surface temperature profile. So we have this two-way coupling between the mid-latitude temperature gradient and the winds. So to try and understand how we might be able to use this to reconstruct past shifts in the winds, we analyzed the PMIP3 and CMIP5 and PMIP4 and CMIP6 climate model ensemble. So the plot I'm showing here, we have the latitude of the westerly winds on the x-axis, which we're terming the wind latitude, and this is the latitude of the maximum zonal mean zonal wind stress. And on the y-axis, we have the position of the maximum gradient of meridional gradient in sea surface temperature, which we term the sea surface temperature front. And this is calculated over a 10-degree latitudinal averaging window. So it's very broadly, where is the steepest part in the meridional temperature gradient, not looking at individual fronts. It's a sort of very broad brushstroke, where is the steepest part of the meridional temperature gradient. We're plotting multiple models from PMIP3, CMIP5, and PMIP4 and CMIP6, represented by the colors, under an array of forcing. So the pre-industrial in the open circles, LGM in the filled circles, and 4 times CO2 in the kind of shaded circle, in the shaded symbols. And so circles and triangles represent PMIP3 or PMIP4. And so what we see is this really, really tight coupling between the position of the sea surface temperature front and the position of the westerlies in the ensemble, suggesting that if we can track changes in the sea surface temperature front, we can track changes in the winds. A couple of points. Firstly, you'll note that the slope of this relationship is less than 1 due to the influence of bathymetry and eddies. The second thing to note is that the relationship that we see in the ensemble is much driven by absolute differences in the climatologies between the models. And what I mean by that is that if you look under pre-industrial forcing, the IPSL model here has very equatorward wind and sea surface temperature latitude compared to the CCSM4 model, which under pre-industrial conditions has very poleward winds and sea surface temperature front latitude. So it's as much driven by the absolute differences in the climatologies between the model as it is by the response of the models to the different forcings. But that does also play a role. So worthy of note, and we'll come back to this later, is you'll see that the 4 times CO2 simulations, most of these sit poleward of their pre-industrial simulations. Okay, so this plot tells us that if we can track changes in the sea surface temperature front latitude, we can track changes in the position of the westerlies. So how can we track changes in the position of the sea surface temperature front? Well, we can use the delta ratio of planktic foraminiferal calcite, good old delta ratio of planktic foraminiferal calcite. So the map that I'm showing you here is the meridional gradient in the delta rating of calcite. And as you can see, it really just looks like temperature. And that's because although it's a function of the delta rating of water and sea surface temperature, at the basin scale, the effects of temperature just totally dominate. So the shape of the meridional profile in the delta rating of calcite just reflects the shape of the temperature profile. And so we can use meridional profiles of delta rating of calcite to identify the steepest part of the steepest gradient and identify the sea surface temperature front. So we compile planktic foraminiferal delta rating records from across the Southern Ocean. All of the sites are shown by the symbols here. And there are 64 records in total spanning the last deglaciation. So let's jump in to look at the data. So here I'm showing latitude on the x-axis and then the delta rating of calcite, of planktic foraminiferal calcite on the y-axis. And these data have been corrected for whole ocean changes in the delta rating of seawater due to ice volume, and also the global mean sea surface temperature change. And although this is very small, and essentially these corrections are just to highlight the local anomalies. They remove the processes that remove these two lines kind of up and down relative to each other, but the whole curve, just allowing us to focus on the local anomalies. So the Holocene data at 10 Ka are shown by the open symbols in gray, and the LGM data are shown by the pink data, the filled symbols, and the modern climatology is shown by the black line. And so what we can see is very clearly this steepest part of the meridional temperature profile, the sea surface temperature front, is shifted equatorward in the LGM, indicating an equatorward shift in the winds. So actually we can quantify how much the sea surface temperature front has shifted between the LGM and Holocene, between these time steps, using a method we developed for the North Pacific, where we just take this curve and shift it. We take the LGM curve and we shift it until we minimize the area between these two curves, allowing us to quantify how much the sea surface temperature front has shifted. And if you're interested in the method, you can read about that in a paper we published last year in GRL, where we apply this method in the North Pacific. But before we do that, it's worth just mapping the anomalies. So here I'm showing that, again, the LGM minus Holocene delta rating O with the whole ocean effects removed. So again, just highlighting the local anomalies. And what we can see is very clearly this anomalous mid-latitude cooling manifests right across the Indian and Pacific. It's equivalent to around a 5-degree cooling beyond the mean surface, global surface ocean change. But in the Atlantic, we see essentially no change, no anomalous cooling, and perhaps a slight warming in the Western Atlantic. So you'll see already that there are some kind of large spatial differences, and we're going to come back to that shortly. Okay, so we can use the method that we developed to quantify how much the sea surface temperature front has shifted at time steps throughout deglaciation, and get a time series of how the sea surface temperature front has shifted through time. And note that the time is going from left to right here. Equatorward is down and Poleward is up. And so when we do that, we get a time series that looks like this. Just to be clear, that this value here is what we calculate as the shift that minimizes the area between these two curves at each of these time steps. So we get this time series of how the sea surface temperature front has shifted over deglaciation, and we want to be able to relate that back to shifts in the winds. So you'll remember that when we looked in the model ensemble, we saw that the slope between these two parameters is less than 1. So we can apply this scaling factor to our reconstruction of the sea surface temperature front to quantify shifts in the winds. But in order to do that, we have to be confident that the model ensemble can skillfully represent the real world relationship between the sea surface temperature front latitude and the winds. Because although this relationship and this coupling is really rooted in the kind of broad scale atmospheric and surface ocean circulation, which these models do pretty well, they are imperfect, and they contain parameterized eddies and relatively coarse bathymetry, which could have an impact and bias the results. So before we apply this scaling factor, we want to really test whether the ensemble skillfully represents the real world relationship. I should have pointed out earlier, but it's worthy of note that the instrumental climatology, so like the measured position of the sea surface temperature front and the winds in the actual climate, does sit on exactly the same line as the models. Okay, so to test if the model has scale in representing the real world relationship, we devised a regional subset test. And essentially it's asking, can the ensemble predict regional differences in the shift in sea surface temperature front latitude from zonal mean shift in the winds? And to do that, we remove subsets of data from different regions. We calculate the shift in the sea surface temperature front latitude using the data from that region. And then we calculate using the model ensemble the relationship between the regional sea surface temperature front latitude in that region and the zonal mean position of the winds. And so what we find is that although these different regional subsets result in different magnitudes of change in the sea surface temperature front latitude in those regions, once we apply the region-specific relationship in the ensemble, they collapse down to a almost identical time series of shifts in the position of the winds. And so this convergence tells us that the ensemble does have skill in predicting the regional sea surface temperature front response to zone and wind shifts in the winds, and it has skill in representing the real world relationship between the sea surface temperature front and the winds, essentially because the bathymetry and the eddies have they vary spatially. So if the ensemble didn't have skill in representing the relationships, we wouldn't see this convergence. So this gives us a lot of confidence that we can apply the relationship we see in the model to our reconstructed change in the sea surface temperature front latitude and quantify shifts in the winds over deglaciation. which is what we did, and this is the result. So again, we have time going from left to right, and the latitude of the winds with equatorward being down and poleward being up. And so what we see is a 5 plus or minus 2 degree shift in the westerlies during the LGM relative to the mid-Holocene. And so there's an early Holocene maximum in the poleward extent. So, but if we take that I'm not showing here, but if we take the mid-Holocene to LGM change, it's a 5 degree equatorward shift in the westerlies. And so what we see is that the poleward shift in the winds over deglaciation just really closely mirrors the rise in atmospheric CO2, which is shown in gray here. It's kind of just quite remarkable how well these two lines sit on top of each other. And so if we do a lead lag analysis, we find an apparent lead in the winds over CO2 of around 300 years, although it's very difficult to quantify the age uncertainties in the compilation due to the covariance of the age uncertainties. So that's tentative. But what this very kind of high correlation between the shift in the position of the winds and atmospheric CO2 tells us it really just confirms the hypothesis that these two things are likely to be very, very closely coupled through Southern Ocean circulation and carbon cycling. And so we wanted to that's apparent already from the reconstruction, but we really wanted to dig in and understand what is the mechanism here, what are the dynamics. And so we wanted to ask, what is the response of the Southern Ocean circulation and carbon cycling to shifts in the position of the winds? And so the reason we want to ask this partly is because kind of coarse resolution models that have looked at this question in the past have been kind of ambiguous as to the impact of shifting the winds on atmospheric CO2. The impact of the strength of the winds is quite clear, but actually the impact of shifting the winds isn't that clear in the coarse resolution models used today. So to try and investigate the impact of wind shift on Southern Ocean circulation and carbon cycling, we utilized a 1/4 degree resolution ocean sea ice carbon model. And so this is a 1/4 degree resolution version of the GSDL model, which has been coupled to a sea ice and biogeochemical model. And so we performed 2 experiments, a control experiment shown in black, where the model is forced with the modern climatology of wind stress in the Southern Ocean, which is shown in black. We then perform a perturbation experiment where we just apply a 4 degree equatorward shift in the winds without changing their magnitude. So these simulations we're performing with this model are really just to try and identify and isolate the impact of shifting the winds on circulation and on the carbon cycle. So a large caveat to what I'm about to tell you and to the results is that these simulations are only run for 125 years because we're running them because it's a 1/4 degree resolution version of the model. But the reason we've opted for resolution, model resolution over long simulations is because we know that resolution really matters to get the residual circulation of the Southern Ocean right. So we can't look, because we only have 125 years, we can't look at the equilibrium response of the deep ocean nutrient cycles, but we can look at the qualitative patterns and kind of get an idea of what the impact might be on the carbon cycle on longer time scales. So what we see is that as we shift the winds equatorward, we see a reduction in CO2 outgassing from the Southern Ocean. And this is driven by essentially a collapse of CO2 outgassing from the polar Southern Ocean. And we can see in the model that this is due to a reduction in the upwelling of carbon and nutrient-rich deep waters. Although CO2 outgassing increases further north, it by no way compensates the reduction we see further south. So we see a net decrease in outgassing of CO2 from the Southern Ocean. So to look at what's going on in the deep ocean, here I'm plotting the overturning rate anomaly of the residual circulation. And this has been normalized for the direction of flow. So if it's red, it's speeding up. If it's blue, it's slowing down. And so what we see is that as we shift the winds equatorwards, we see a slowdown in the deep ocean globally below 2 kilometers. And what this does is it just increases the carbon storage in the deep ocean. This is the horizontally integrated DIC profile. And so we can see that just carbon storage in the ocean increases as the deep ocean slows down due to this 4-degree shift. And so to try and get a handle on what the implications are for the carbon cycle on longer timescales, and if we kind of think back to preformed nutrients that we were talking about at the start. So if we look at the surface nitrate anomaly between what we see is that with an equatorward shift in the winds, we vastly reduce the nutrient concentrations in the polar Southern Ocean because of this reduction in deep water upwelling. This results in a substantial decrease in the preformed nutrient concentration, which is what I'm showing here, of Antarctic bottom water. This is and so you can see these low preformed nutrient anomalies starting to propagate their way into the deep ocean. We only have 125 years, so they're never going to get there in 125 years. But what we can do to try and just kind of get a rough approximation of what the implication is of this 4-degree shift in the winds for CO2 is we take the changes in the end members and just extrapolate those based on the volume of the ocean they represent. And then we can use the scaling based on Ito and Follows and others to estimate the impact of these changes in preformed nutrients on atmospheric CO2. And so the changes we see are equivalent to around a 15 ppm decrease in atmospheric CO2, which would be a long-term decrease. So it's quite striking that just a relatively small 4-degree shift in the wind can have such a large impact on the overturning rate of the deep ocean and oceanic carbon storage and CO2. So to finish, I kind of want to dig a little bit into the dynamics of what we think is going on, and essentially ask the question: how can the deep ocean, how can the residual circulation of the deep ocean and the carbon cycle be so sensitive to small changes in the position of the winds? So we think it comes down to the presence of the Drake Passage in the Southern Ocean. Particularly, we have this zonally continuous channel above 2 kilometers depth at the latitudes of the Drake Passage in the Southern Ocean. And this favors waters from below 2 kilometers as the mass replacement to balance the Ekman divergence south of 60 south. So to the south of the Drake Passage, because we have this zonally continuous channel, waters from below 2 kilometers are privileged to upwell to balance the Ekman divergence we have south of 60 south. Now, this privileged pathway of deep waters is lost as the westerlies shift equatorward. So what you'll see is that while the overall Ekman divergence, the amount of water that needs to be replaced, increases as we shift the westerlies equatorward in the Southern Ocean, the Ekman divergence in the polar Southern Ocean south of the Drake, below 60 South, essentially collapses to zero. So we lose this privileged upwelling pathway of deep waters. And so this is what drives the slowdown in circulation of the ocean globally below 2 kilometers. And so we really think it's this this kind of interaction of the Ekman flows and the bathymetry in the Southern Ocean that gives us high sensitivity to relatively small shifts in the winds. Okay, so just to finish up with the conclusions, we can use meridional profiles of planktic foraminiferal delta 80 to track the latitude of the sea surface temperature front and the westerly winds. We find a 5 plus or minus 2 degree equatorward shift in the Southern Hemisphere westerlies during the LGM relative to the mid-Holocene. We see that the poleward shift in the westerlies over deglaciation very closely mirrors the rise in CO2. And using a 1/4 degree resolution ocean carbon cycle model, we show that shifting the westerlies equatorward increases oceanic carbon storage. So taken together, our results clearly indicate an important role for the westerlies in driving the deglacial rise in CO2. And to kind of to extrapolate our findings and these sort of dynamics into the future. So we saw on the plots of from the climate model output and we observe today from the instrumentation that the westerlies are shifting poleward and are expected to shift poleward under global warming. And so what our results would indicate is that as they do this, natural CO2 outgassing from the Southern Ocean is likely to increase and act as a positive feedback on warming. So thank you very much for listening. Before I answer questions, I wanted to point out that if you're interested in this and interested to read more, we have this work is currently in review, but we do have a preprint available on Earth Archive. So if you can't find it, you just email me. I'll be very happy to share it. But thank you all very much for listening.